I was gonna say, well, I bet the only way a girl will go out with you is she can finish a Rubik's Cube in 5 minutes or less.
No, there's no qualifying test.
Sure?
You probably have like random equations on the napkin.
Now, have you guys met Mr. Malachek's girlfriend actually?
No.
You haven't met her? She's been here. Have you seen her walking around?
No. Oh wait, yeah.
She's a chemical engineer who's in med school. She's very smart. It's not an unattractive thing to be smart.
Did she fail your Rubik's Cube test?
Anyway, let's start the topic of linearization. So we just wait Houston now. It's the only one now. The is she you still?
Yeah, she's all just now.
Can I talk to her real quick?
Hey, Miss Wanda.
I just missed her call.
She'll go.
What's in your
Is it gonna get wild? You
I don't
know?
know.
What's getting wild?
I'm
To me, it's a whole different thing.
Go, but tell her you got class. She knows this stuff. After school, you guys have class. Thank you. All right. So the topic is linearization. Again, what we're doing here to start is taking a look at curves and how we can approximate them as lines on a small scale. So if I had a normal curve like this that had, let's say, some sort of a cubic function with a bit of a dip, so we're looking at something maybe a fifth order function here. If I wanted to approximate this with lines, I could put a bunch of lines over it. So I could approximate this portion right here, maybe with a line from here to here. Then I might want to approximate the next portion, and I'm going to show with colors, from here to here. Then I might call this another line from here down to here. Again, notice what I'm doing. I'm looking at all the tangent lines. And I can approximate this pretty much with an infinite amount of lines. You can always do that. There's another line from there to there. Then another line from here to here. Then another line from here, maybe over to here. And you don't have to do all these lines, guys. I'm just showing you.
Does this lead to like the second?
Yes. Yes. Differentials. It will lead us to differentials. This is the last, or second to last topic. There was a topic that I love called Newton's method that is not on the AP test anymore. So we're going to do it, but I'm going to wait till after the test. Just to save time, okay? Because we need to worry about that test itself.
We're gonna have class.
We have a month after the test. So we'll be doing some extra topics, some cool stuff. I'm going to try and bring in experiments we can do. That's the goal for that next month. So again, taking a look at this curve, we can see that you can always approximate it with an infinite amount of little lines over it, okay? And that's what a curve really is. If you remember from geometry, a line is an infinite amount of points. So a curve is an infinite amount of lines. Okay, it's like having a ton of lines over and over each other. Now, if I got to the point where they got smaller and smaller, they'd be called something called differentials. And we'll talk about that in a little while, which is like dx and dy. Those are differentials. So, for this one, what we're going to do today is look at one example really, okay? And there's not a lot of questions on this in your test at all. I've only ever seen like one multiple choice on this whole topic. So it's not that important that we spend a lot of days on it. And it really isn't that important besides the fact that it kind of leads into the next topic. That's where it's important. So, let's start with an example. If we have the function f of x equals 1 plus sine of x, and the graph
Looks like.
I'm not going to show you what the graph looks like yet. The graph, or the part we're going to look at here, is between negative half and positive half. So from the interval negative 0.5 to 0.5. That's my x domain.
Isn't it shifted up one? Oh yeah, that's all it is, right?
That doesn't make a difference.
Yeah, it's a sine curve shifted up one. That's all it is right now. But what we want to do now is take a look on this interval from here to here, how we can approximate this with a linear function. You know why? Because linear functions are so much easier to deal with than trig functions. And a trig function is a bunch of linear functions combined over and over again.
So you're going to say it makes pre-calculus easier, right?
So yeah, that's exactly it. It makes curve sketching and graphs easier. So the way we can do this is as follows. We can approximate this by taking the derivative at a point, just like we've done many times before. So what you want to do here is approximate f of x by using the equation of the tangent line at x equals 0. Why am I choosing x equals 0 here?
At the origin?
Yeah, and take a look at your domains. It's the middle, really. It's the middle, okay? And in a minute, you're going to see how clear it is once I draw the graph, but I don't want to draw the graph yet, so you can wait on that, okay? And it really does help. So, the derivative. What's the derivative here? Very good. No dx anymore, right? Don't forget, we're not doing implicit anymore. Back to regular.
But there's nothing to write 0, is there?
I know, you do not need to write
Oh, okay,
zero.
I was just saying in this topic, do you need to?
No, sorry. I'm just showing it, but that's a 0. So, the derivative is cosine of x. If I want to know what the tangent line is, equation of the line tangent, or the tangent line, I have to remember to think about y equals ax plus b. Or we can use y minus y1 equals m times x minus x1. Remember, there's 2 ways to write lines.
Y equals x.
Like that. And if you remember from geometry, we called that m for slope, but I'm calling a slope here. Remember, we're calling a slope, not m anymore. A is just more simple because we're thinking about a polynomial. A, B, C, D, etc. So, for this kind of a problem, we all good?
Yeah.
Okay. Try and get caught up because we started. So again, we're approximating 1 plus sine of x here from -half to a half at the origin we're looking. I'm sorry, not at the origin, but x equals 0. I don't know if it's the origin just yet. Now, if I can figure out the derivative, which I've done, we've got cosine of x. I want to know what is the tangent line. What is the tangent line? So, a represents the slope. Well, here's the slope, cosine of x. But at the point 0, what's the slope? If I plug in a 0 here, what's cosine of 0? 1, right? Again, the derivative at 0 here, at 0 is equal to really just the cosine of 0, which is 1. So, the slope,
please come to the Ministry office at this time. Adolfo, Sergio, come to the Ministry office at this time. Thank you.
the slope, sorry, scratching. The slope here at x equals 0 is simply 1. So that's what's going to go in for a right here, okay, for my tangent line. So I know that this is going to be 1. So whether I use this point or this method or that method, it does not matter here. But my tangent line slope is 1. Next, I want to figure out the value of the actual line. So I still need to know what b is. To get b, though, don't I have to plug in for x and y?
Yeah, if you plug in the original.
I know x is 0, right?
If you plug in.
What should I do to get y, Getty?
Plug in the original.
Very good. If I want to know what y I'm going to plug in, I can plug in a 0 for x, that's fine. If I want to plug in for y, plug in the 0 up here. Sine of 0 is 0. So this is just going to be a 1. So my point is x equals 0, y equals 1, really. That's the point I'm going to plug in to find b now. So plugging in here to find b. If you put a 1 in here and a 0 in here, you're going to get 0 times 1 is 0. So b just equals 1. Same thing down here if you did it. So again, our line here is going to be y equals 1x plus 1. That's going to be my equation of my tangent line. And this should all be a review. This is all review from just derivatives so far. That's all it is. Now, the cool part is taking a look at the graph now. So, x plus 1 is just a line, right? It's just a line at the point y-intercept, of 1. So if we're to graph this,
No, it's 1 and x.
no, it's not absolute. That's a 1.
Absolute, though. It's funny.
That's a 1x.
Absolutely x plus.
Yeah, x plus nothing.
1x plus 1. Okay? I know I don't have to put the 1. I put it there to denote it because we got 1 for a slope. I wanted to make sure we know that that was the slope. So the equation is y equals x plus 1. If we were to graph this, here's what we're going to see. And this is the cool part again. Y equals x plus 1. Okay, there's just a line. That doesn't do any good for me. But we're going from where to where?
-5.
So we're really looking at this location. Between here and between here. So this is the portion of the graph that we are really focused on. You all see?
Yeah.
And now, again, what did we say a minute ago? We said that if we're looking at a curve and we look at a small portion of it, we can think of it as a line. So if I'm able to superimpose the other function on top, so 1 plus sine of x, which is what we started with, I'm going to put that on top of here. So I'm simply going to type in y equals 1 plus sine of x. And what you're going to notice is, take a look. Between negative 0.5 and 0.5, aren't they pretty much identical? So this is a wonderful approximation for this. But what happens as I go further out?
It's nowhere close.
It's nowhere even close. So what we can see is that the idea of looking at a line instead of a curve only works in certain ranges. So if I were to write this sine curve as a piecewise function, the piece of the function from negative half to half would simply be the line here, the line x plus 1. That's the piece of the function that matters there. Once I go outside of 0.5, look at this differential, or look at this deviation here. It's a huge deviation, and it's going to become larger and larger and larger. So this only works in certain domains, okay? So on your AP exam, the kind of problems they ask is the following. They'll say, approximate the curve between 0 and 1 of the function f of x equals, and they'll give it to you. And you know what you do? You do the same thing we just did. You're finding the equation of the tangent line, you're locating it as a piecewise function, and you can even show it as a graph. That's all this is for linearization. Are we okay so far?
Non-calculator section?
This would be a non-calculator, absolutely. Non-calculator or multiple choice. That's the only time I've seen this topic.
Do they have to give you the range, or you would find the range?
They're going to give you the range, but you know what, Kenny? That's a great question. They might say, within what domain is this a good approximation?
You would have to draw you would have to get the line, tangent line, and the graph, and find.
Absolutely. So here, if we were not given negative 0.5 to 0.5, take a look. I would argue that it might even go up to like 0.8. And this might go as far back as like negative 0.8 or 0.7, whatever it is. But if you guys are going to approximate this on your own, you find the tangent line, you find the actual curve, graph them simultaneously, look on your calculator to see where they overlap. And where do they overlap so that they are actually no deviation? The minute you go beyond these points here, you're going to see that the deviation gets bigger and bigger. So this deviation is small, this is bigger, this is even bigger, and so forth. So where is this answer reasonable? Between negative half and positive half. Is that clear? Okay, let's look at another example. I'm going to make it up here. Okay, so let's make up an example now. Okay. Now, if we're going to make up our own example, let's start with a function that is, I don't know, give me a random function. Exponential. 2x plus 1, linear. Let's go a little bit higher. So like squared or cubed or something.
5x squared plus 2x squared.
All right, let's go with combination of exponential and squares. Let's take a look at this. Okay? Now, what I want to do is the following. I want to approximate this curve with a tangent line around the point x equals 2, and then give a domain that makes sense. So we're not going to give the domain this time. So again, approximate this with a tangent line at x equals 2, I'm telling you that now, x equals 2, and see how far from 2 is it actually true. Remember how for the last example here, it's kind of true away from 0, half a unit left, half a unit right. After that, it's not true anymore. So we're going to be looking at 2 and go left and right and see what it looks like. We'll do it algebraically, and then we'll check with a graph. Is that clear? Yeah. All right. So first thing we need to do, take the derivative, and where are we evaluating the derivative at?
2.
Good. At x equals 2. Derivative of 5x squared. Derivative of e to the x.
Plus dx.
Very good. It's a repeating function. It doesn't do anything. So there's my approximation. Okay, there's my approximation. Again, for the derivative. That's not the derivative line, though. This is the slope of the derivative, or the slope of the tangent here. We now have to plug in the 2. So e squared, e is 2.71, squared is 8 and change, so we're looking at around 28 or so as a slope. Again, we're looking at a slope of 28, which makes sense, because think about this function. Isn't this exponential growth? Look at the slope of my hand right now. What's happening to it? Slope is going up. So a slope of like 28 or so is a reasonable thing. That's how we can check in our mind this. Now, continuing, that's my slope right here. I can put a decimal representation if I'd like to, but it doesn't help that much. Now,
should you get rid of the e squared component so you can make it all one value?
That's what I just said. I said I can make it a decimal representation, but it doesn't matter right now.
Oh.
So, if I want to use y equals ax plus b, I know a. A is this value. I want to find b. To find b, I need x and y. I got x. Plug a 2 in here, get your y value. So when you plug a 2 in right here and here, 2 squared is 4 times 5?
25.
20 plus e squared. Take a look for this one. It happens to be the exact same thing. A little bit of a coincidence there. Okay, just a simple coincidence, nothing more than that. So, the slope, the y value turns out to be, when you plug in a 2 here, 20 plus e squared. So, over here, we've got 20 plus e squared equals, parentheses, 20 plus e squared, complete coincidence. The e squared is not really a coincidence, okay, because it's a 2, but the 20 happens to work out. If I chose 3 instead, it would have changed this number a lot. It would have made it 9, which is 45, and it would have made this 30. So it would have been 45 and 30, very different. So I know the x value is 2, and I'm solving for b. Again, y equals ax plus b. This is the line that is tangent. A is just simply the slope of the derivative. So I take that value, plug that in for a. I know the x value was given as 2. I want the y value over here. So I took the 2, plugged it in here, got the y value, and now solve for b. Okay, so if you think about it, if you double this and then subtract double it, it's going to be negative that value. So it's just going to simply be negative 20 minus e squared. Again, this is like saying I have 4 over here and 2 over here. If I subtract 4, isn't it just going to make it negative 2? So since this is one number and this is double that number, when I subtract it, you're going to get the negative of this number. So going down further, I'm going to get b equals negative 20 minus e squared. Okay? I'm leaving e squared for a minute just because of its exactness. On your test, on your multiple choice, they'll leave it in terms of e and pi. They're not going to evaluate always. If it's numerical with a calculator, then you'll probably have a decimal.
If you were doing, so if we're ever doing derivative of e, we should just leave it as e?
But it all depends on the question. It always depends on the question. If the multiple choice has answer choices with e in it, yes. If they're all decimals, no. God bless you. God bless you. So here's your line. 20 plus e squared times x, that's the slope, and then here's your b value. So I'm going to put minus 20 minus e squared. There's your tangent line right there. Now, if I graph the original function and I graph the tangent line on the same graph at x equals 2, I should notice that they're pretty much the same. And I want to see how far will they be the same. How far to the left? How far to the right? Okay? So here,
but how do we
your answer is going to be a domain.
Is okay.
An interval.
But how are we gonna be the same?
We're going to graph it. That's how we're going to do it.
But could you ever graph it and have it not be the same?
No, because remember, the tangent line is at the same point as the curve, remember?
Yeah.
Draw any tangent line, it touches the curve once, right? So they will be the same on that point. It's how far to the left and right are they the same.
Yeah, that's what I was wondering.
That's a very good question, guys. That's exactly what you want to be thinking about. Remember, the last example we did, they were identical here, weren't they?
Yeah.
They were exactly identical at 0, 1. But after that, they became a little bit spreading out.
You can have a parabola, and it only
yes, exactly. And that's what we're going to try and do now. So here, we got 20 plus, now e you write as exp, parentheses. Exp just means exponential. And notice we said numbers around 28, 27.39. And this is going to be minus 20 minus exp squared, close, close. So it's pretty much, ooh. Thank you, Karen, you're right. 20 plus exp 2. There it is. I put minus minus, right, on the board? Take a look.
Yeah,
Minus minus is the same thing as having a plus with a parentheses around it. That's all I did. I just distributed the negative. If you had negative 20 and negative e squared, it's negative 27. Yeah, I have to put the original still. So this,
would you want us to back out the negative or leave it as is?
doesn't matter at this point because now you're graphing, so it's up to you. If you leave it as is or factor it, it's the same graph.
Why did you change it?
It doesn't, because it doesn't make a difference. I don't know. I really don't. It was just a common habit. Now, take a look here. This is the line 27.39x minus 27.39. So my y-intercept is all the way down here. All the way down at negative 27. Okay, that's where my y-intercept is going to be. So if I scroll all the way down here, if I ever can, make it there. There's my y-intercept at around negative 27. Now, the slope is so steep. How come again? Exponential. Go back to the original function. If the original function looks exponential, it looks like this. The slope over here is very steep. The slope over here is not very steep, but we are over here now. So now I want to graph the exponential function. Come on. Okay. The exponential function we'll call g of x, and that was equal to 5x squared plus e of x, or e to the x. So, at first, it doesn't look like it helps, right? But where are we looking at? At the point 2. So I have to follow this all the way up. So clearly I got to move up on the graph. So let's scroll down until we get to 2. And take a look. At exactly 2, it's identical right here. Around 27-ish. That's what it should be. And what you're going to notice is this. It's almost identical until where? Until it gets to like right here. See where it splits? See how it kind of like starts to split right there? And you see one graph goes this way and one graph goes that way? So until this value right here, which is approximately 19.5 for the y, and on the x it might be like 1.8, until it gets 1.8, anything beyond that, it starts to split off. And on the other side, so again, let's write that down. So on the left side, it's around 1.8 when it starts to break off. So my range, or my interval I'm going to be looking at is around a positive 1.8. Now I go back to my graph. I go all the way up until I get to, again, where they intersected at 2, right here. Then I keep going up, and where do they start to split? It's a little bit like, maybe like right here. You see all that? You can barely see it. Again, you can barely see it. So you know what you might want to do? You might want to zoom in. You might want to zoom in between like 1 and 3.
No, Ken,
Okay?
I said zoom out so you can see where it was.
Well,
No, I said
you need to zoom in on the x and zoom out on the y. That's what you have to do. Trust me. Watch what I do.
I know, but yeah.
Zoom in on the x, be nice. So let's say we're going from 1 to 3. And along the y-axis, let's go from, let's look at the graph already. So we can see how they start to split there, right? So let's go down a little bit further. Okay. So, take a look, people. Take a look. Here is 2 right here. Here's where the actual x equals 2. And we're going from 1 to 3. Okay, we're going from 1 to 3. So this is 1 out here. This is x equals 2. This out here is x equals 3 right there. Okay, I know we're really zoomed in. We're zoomed in between 1 and 3. And what you're going to notice is, as you zoom in further, they start to split closer. So they start to split pretty much here, and they start to split pretty much over here. And what you're going to see is that this, if this is 2 and this is 3, these are going by fifths. Everybody see that?
Yeah.
So our approximation of 1.8 was pretty darn good. Because this is 1.8 right here. That's the line 1.8. This is like 1.85. And this is like 2.15. Again, this is 1.8. This is 2.2, 2.4, 2.6, 2.8. I'm going up just to show you it doesn't have to go up like that. But again, those lines are increments of 0.2s. So it starts to split a little before 2.2. It's probably around 2.15. And this is probably really around 1.85 right there. So when we go back to our solution, we might want to change our interval. Instead of 1.8, making it 1.85. And going all the way to 2.15. So this tangent line is a good approximation of the curve between 1.85 and 2.15. Again, it's only a good approximation from here to here. Okay, everything else, take a look. It starts to really split off. See that? This tangent line is only a good approximation in this little area. Where is this area? This area is between here and here. Well, a little further, maybe over here. Between 1.85 and 2.15. Christian.
Is there a way to find the best tangent line?
Is there a way to find? They're all the same.
They're the most accurate.
Yeah.
There is no more or less accurate. It depends on the location you're at. Because if you were here, not at x equals 2, then the tangent line looks like this, and it's going to change the function completely. It's all about where is the tangent line actually usable. It's usable in between here. Outside of there, the tangent line doesn't really help us.
Well, is there like a single tangent line that has like the greatest amount of...
Is there a way to optimize the range at which the tangent line is acceptable? Not that we're going to be doing, and not that's even usable. It's not worth it. That's what I'm trying to say there. Jasmine.
Can you say this is some collection point or like a collection point since they're like right, like the same?
Can you say it's an inflection point? It's not an inflection point, it's more of just an intersection. Don't confuse that because, again, inflection point really means change in concavity. So it's concave down and then concave up. This, if we zoom out a little bit, if we zoom out of this graph a little bit, let me zoom out and show you what I mean. As we zoom out here, what you're going to notice is that the original graph is always concave up. So there is no inflection point, but there's really an intersection there. And then on the left, it's acceptable for a little while, and on the right, it's acceptable. But notice what happened, guys. Notice, here's your point right here. Here's your point right here. It's still pretty much the same answer. 1.85, 2.15. And you know what you can do? You can actually figure out those exact locations. Because you know the y value here. You can figure out the y value there if you go over it. You can figure out the y value there. If you know the y value in those two spots, you can go to the derivative, plug in the y value, and find the x values to find the exact location. Kenneth?
Well, you can't really get it. I mean, it doesn't be
exact. Exact based on your estimation.
Exactly. There you
Oh,
go. Okay, and
Is it exactly?
Yes. Wow. I was gonna ask you. But in other than leading to like the next topic, what is this used for? Exactly.
If you don't want to use complex functions, you approximate them as lines. So for example, if you have exponential growth along with the trig function and something else, you use the derivative to approximate lines because when you use computer programming, it's easy to use a derivative program if they're linear. When they're non-linear, when there's stuff like this, it's much more complicated.
Yeah, but do you do like thousands of times?
No, you don't. You can write programs that do this for you. So you can write a program to then use in another program, which is like an embedded program. That's all it is.
Inception.
Okay, so you can find the derivative in several different spots, and you can write a program to do that for you that gives you a different interval for each one, and then use that new piecewise function to actually look at that. But you know what's interesting? Whenever you're looking at a function, you really only care about one location. So we really only care about this location. If the person was looking at like x equals 7, it would change it up completely. So it's going to constantly change, yes. Okay? But again, it's just a technique. We're going to use it with differentials in a minute. Everybody okay? We're coming.
On the exam, are they looking for like really approximate answers, or are they just looking for a range?
For the exam, either they're going to give you the domain to look at, okay, and say find the tangent line that works in this domain, or they might say find the tangent line that approximates this near 2. How far is the precision? Let's go through what that means now. Anybody know what precision means?
Precision, accuracy. No.
Everybody thinks the same thing. Here, simple example, and this is one that people don't even know. You got a dartboard, okay? So start with a dartboard. On a dartboard, or let's say a bullseye to make it even easier. A bullseye, we know, has several rings until there's the bullseye in the middle. Now, if I throw 3 darts, one here, and one here, that's actually very accurate because the average of those darts is actually the center. You're with me right now?
Wow.
They average out to be in the middle, whereas 3 darts thrown like this are precise because they're grouped. Precision has to do with the grouping. So these are precise shots, whereas these 3 would be accurate shots.
So like precision is like getting them all. Precision
Precision is consistency, really. So here's where this comes into the next topic. Precision. If I were a manufacturer and I was building something, which is what many of you guys will do if you study engineering, you'll learn how to do production processes, which are very important. You can make a lot of money doing this, by the way, a real lot of money. It was one of the fields that I looked at when I was in grad school that I was very good at. It was boring.
No health insurance.
So the idea of precision is this. Imagine if I was a manufacturer of ping pong balls, okay? No ping pong ball is the same as the other. There's always some sort of mistake or deviation, okay? The deviation has a with a limit to it, a limit above and below. For example, here's a ping pong ball. It's 3-dimensional, so we'll draw a sphere. We'll say that the goal is to have every ping pong ball with a radius of 0.75 inches, just because it's a little more, I think. So let's say the radius is 0.7. Actually, you know what? 0.5 is better. 0.5 is more accurate. The diameter is about 1 inch, I'd say. So the radius is probably about 1/2. You're closer. So the goal is to have 0.5 as the radius. Is every radius going to be that? No. They're going to be off by a little. So One radius might be,
Jasmine Guzman, if you're still in the building, come see Ms. Kerrigan. Jasmine Guzman, if you're still in the building,
She's not
come
in
see
the
Ms.
building.
Kerrigan.
tell them I need to talk to Ms. Fontanella and Ms. Kerrigan later in a nice way, but tell them I need to talk to both of them
What
later.
we do is make a scalpel outside the
I
window.
promise, Jasmine, it will nothing to do with you, but tell them I need to talk to both of
Make a
them.
scalpel outside the building on the window. and
Thank you.
Have Jasmine stand the scalpel so she's not
All right,
exactly
so-
inside the building.
Let's say we happen to measure a radius of one of the ping pong balls that is produced, okay? We measured one of the radii of the ping pong balls, and we noticed that it's off by a little bit. But is that off by a little bit? It's very, very little. So the precision would be 0.0001. I'm sorry, one more zero. Because again, subtract 0.5 from 0.50001. The 0.5s drop off. This is the precision. It's off by not a tenth, not a hundredth, not 1,000, not a 10,000, but 100,000th of an inch, which means nothing really. It's almost nothing at all. But when it comes to machinery and making stuff, it does mean something. So for example, if you anybody know what a ball bearing is?
Yeah.
Like a socket and ball and socket joint? So your leg, for example, how come you can rotate your leg freely like this? There's a ball here really, it's your bone, but it's a ball and socket joint. There's a socket, the ball sits inside of it, and it can rotate freely. You have limitations, obviously. Now, when you're building things with ball bearings, it is very important that the ball bearing, which would be like the end of your joint, or the end of your bone, your femur, is exactly the size of the case that it's in. So imagine you had a ball bearing case like this, and there's the ball bearing attached there, so that this can freely rotate. This can move back and forth. If the ball bearing is not precise with the amount of deviation, correct, it won't rotate freely. And you'll notice, you guys, you wonder why you pay so much for Bose speakers and all that kind of stuff? All the technology in that is extremely, extremely precise. That's why it's such good sound. That's why you pay more money for this stuff. So for example, if I had that rolling chair right there versus the rolling chair I have at home, the one I have at home, I have a really nice rolling chair. Just because I use it a lot. I'm sitting in my chair a lot doing a lot of work, so I want something that's very comfortable. So that chair might cost like $50, whereas the one I got is a lot more than $50 because the precision of all the different parts of it are extremely accurate. So what we're looking at now, what we're focused on now is precision. So here's what this means now. If we go back to our example, if I put a point here and a point here, again, there's my 2. How far off was this point again? What did we say? And this one was 2.15, right? Notice, what did I use on each side? So my precision is plus or minus 0.15. Because again, where was my target? My target was at 2. My target was at 2. The derivative is good until 1.85. And the derivative is good until 2.15. Do we all see that?
Yeah.
So it's good 0.5 below and 0.5 above. Thus its precision is plus or minus 0.15. Okay, we're going to use this with differentials. It's good that you understand what we're doing here.
How would you do that?
Say again?
How would you think that?
How would you make that assumption?
No, think like it's precision.
If the problem asks to what precision is the derivative a good estimation or the tangent line a good estimation, here's your precision. And it will give you a multiple choice probably. And that would be your answer there. Does that make sense?
Yeah.
This would be like your choice here. It's not going to be a free response. That's kind of a problem, Edgar. It won't be a free response here. Okay? It's going to be like a multiple choice. So if they ask you for an interval, 1.85 to 2.15. If they say, how precise is it? To what values of x is the precision? Plus or minus 0.15. Okay? Precision versus an interval here. Two different things. Questions on this? Okay. Let me see if I want to continue with the next one here first.
Priscilla LaBelle, please report to the main office. Priscilla LaBelle, please report
We'll just, to end the day, we're just going to try one together. That's all I want to do here. Okay? Try one together. I was going to go on to differentials, but we'll do differentials tomorrow. Differentials are just as easy. That's all it is. Stuff like this.
So will this one have, in this problem, will we be dealing with precision?
Do what?
Will we be dealing with the precision?
Sure. We'll do precision at the end. We'll look at the interval, and then we'll talk about precision. I would like to. I would like to.
I don't care if you're talking to me. Hey, I can believe it.
Relax. Relax.
Like an old married couple.
Oh, maybe,
Maybe we should put one of y'all, like on this side, and one of y'all on
It doesn't matter. So you're telling me that married couples are meant to be separate?
Now,
I'm telling you that you
if
Statistics tell me, Kenny.
f of x is equal to x cubed plus cosine x minus the natural log of x, okay? We want to find the equation of the tangent line. Let's say for this example at x equals, not 1, because that'll screw up this part, I think. Let's say at x equals pi over 6. Why am I using pi over 6? Because the cos, it's 30 degrees. Cool. Jess? Now, we're approximating here. We're approximating a tangent line again. So what do we do first? Derivative. Again, at the end though, we're going to need a y value, remember. We're going to need a y value also. So if you'd like to, plug in the pi over 6. Use your calculator here.
1 over.
Okay? Again, what I'm doing though, notice what I just talked about. You can find the derivative, but we're going to need the y value later. So if you want to start by plugging in the y value in these 3 spots, that's fine. And find the y value. Thank you. The x value to find the y value. Thank you.
I mean, like, so why either or? I mean,
Doesn't matter.
Yeah,
Doesn't matter.
Fine, no.
I'd rather find it.
Now, what I want you guys to notice is this. When you plug in pi over 6, you definitely want to use your calculator here. Okay? Again, you really want to use your calculator. It doesn't really matter. We can leave everything in terms of natural logs and cosines, but it will become very messy. Does anybody want to do this for me? Just plug this into y1. What is it? Thank you. 1.65. Again, how did she do that? Plugged it into y1. She went to the table, plugged in pi over 6 into the table for x, and that's what you get for y. I trust that's correct. I hope others can check, please. Now, for the derivative. Yes. Can you come back in about 5 minutes? So, 3x squared. Now remember, derivative of ln is 1 over x. Derivative of ln is 1 over x. If we wanted to make it harder, I should have probably made it x squared. I'm not going to yet, but if you wanted to, x squared, and you need the 2x for the chain rule. Don't forget that. So, here's my derivative. Here's my derivative. Find the derivative at pi over 6 now. Again, don't do this by hand. Put the derivative into your y2, type the derivative in, or just use n deriv in y2, and find the derivative at that value. Or put this in y1 and use the dy dx function. Remember, if you go to y1 and plug this in, you can press second, calculate, and then go to dy dx and plug in pi over 6. Again, you can always find the derivative at a point without actually calculating the derivative. You can plug this into y1, go to second, calculate, go to dy dx, type in pi over 6, and it'll give you the derivative at pi over 6.
I'll give you the slope, right?
Thank you. The slope of the derivative. Thank you. So again, you can do dy dx, so second, calculate, go to dy dx, and then type in pi over 6. Make sure you're in radian mode.
Alright, so plug in x.
We've actually had a conversation with a cashier about that.
Really?
What's the difference between that?
You plugged in the original, right?
Yeah.
Are you sure?
It's just like really obvious. Come on, no.
No, you just
go
to 1. It's
right?
not correct. I'm sorry. So now for second calc, go to dy dx, type in pi over 6, second pi, divided by 6, enter. Derivative is negative 1.58. Now,
you messed up.
guys, I hope you're all trying this. I don't see everybody trying it, but this is stuff you have to do on the AP test. Now, the slope at pi over 6 is this value.
Where do you have y?
The x value is here. The y value is here. So when I go to solve here, just plug in to find b.
Do it analytically. Just type.
For the y value, you've got 1.65 equals negative 1.58 times pi over 6 plus b. That's a 6, sorry, pi over 6. So everybody take 1.65 and subtract the product of these two things from it. I'm sorry, add. It's a subtraction. Again, so multiply this by pi, divide by 6, add it over here to get b by itself. It's got to be positive.
It's got to be less.
Yeah, it's positive.
Did you get negative 1.99 for this, Karen, right
You know
here?
why I didn't use parentheses?
Ah, okay. Again, remember 1.58, parentheses, pi over 6, close parentheses, enter, then add that to 1.65.
Oh, hey.
Just positive when it goes.
Because you're adding it, yes, correct.
Oh, the derivative was.
Again, guys, she's the only one doing this right now. Let's go. Other people need to do this. Sorry, others. What do you got?
0.822.
So, the B value is 0.822. Alright, so I've got the A value here. That's my A value. That's my B value right there. So I've got my line. The line that will approximate this function at x equals pi over 6 is now y equals negative 1.58x plus 0.822. There is my tangent line right there. Again, because I got the slope from the derivative, I got the x and y value, I plugged them in to get b. So now, using that right there, using that, let's just graph it and look. Negative 158. What's that? It's not really?
Tomorrow I'm just going to be slamming my head on my desk. Hating my life.
2.47. That's all right.
This video on screen.
So correct that, please. It's 2.47. But again, you need to check this, guys. That's why I asked you all to check each other. So, 2.47. So negative 1.58x and 2.47 equals negative 1.58x plus 2.47. That's my line. And we can see clearly already, it's a negative slope. It's a negative slope. So this is the line right here. See how flat that line is? We're looking at pi over 6. Where's pi over 6 numerically, approximately? What's 3 divided by 6? It's about a half, right? Everybody see that? 3.14 divided by 6 is around a half. So we're going to look right here. Well, I got to put the other function in still. So go up to the first function, type the original in. And the original, x cubed plus cos x minus ln x. And take a look, guys. If we zoom in enough, you're going to see the natural log function curve like that. And see that little spot right there? So let's zoom in on that spot. And again, we're really far zoomed out. That's why this doesn't look that good.
But Mr. Allen, since one is negative and one is positive, oh, definitely.
It doesn't matter. It has to do with the slope. So the slope is negative, and that's positive. That's the y-intercept.
No,
That's all
I'm
that
talking
is.
about since one. I'm talking about since one slope is negative and one slope is positive. But at that point, that slope is negative.
Yes, very good. This is a negative. This is a positive slope. That's a negative slope, but the limit of the slopes is the same as you go to that value. So pi over 6. Where is that? What's the exact value of pi over 6? Can somebody do second pi or over 6? And just to get an exact value. 0.523? Okay, so here's our point, let's say right there. That's where they're going to be in contact. Now, to the right, I can go maybe up to here. I'm sorry, to the left. To the right, I can go maybe over to here.
0.25.
Would you agree? In that range, it's pretty much the same line. Outside of there, it's not. So, Kenny, what do you want to use?
0.25.
Good. So, 0.25 to 0.75. That's my interval on which the line is a good approximation. Thus, my precision is 0.25 plus or minus. This means a quarter to the right and a quarter to the left. This is a pretty good approximation. Is that clear?
Yeah.
Last question. Go.
Are those equal?
No, they're not. And it has to do with even and odd functions. But in this case, I'm just simplifying it. But yes, this one could have been a little bit closer. Again, it's an approximation. It's an approximation. Tomorrow, guys, well, no.